coffee break. We now move into our most exciting part of today's session, basically the Google's workshop on training LLMs using TPUs. Please join me we have offline Mr. Srinath and Mr. Srikanth and Mr. Robert Dyro will be joining us virtually. Please have a big round of applause for all of them.
Robert, my colleague, he's also on the Zoom meeting. I'll be presenting first, and then Robert, followed by Srinath, who is there in person. Hello, everyone. Good morning. I'm very pleased to be able to talk to you today about Google, and I'm joined here, Google's AI hypercomputer, what we offer in the cloud, and especially our latest generation TPU. I'm joined by my colleagues, Robert Dyro and Srinath, who is there with you in person. I deeply regret that I was not able to join you in person. ISC is a very special place to me. I love the campus. I've been there a few times. And I wish I was able to join you in person. But before I start, I want to make sure that you all can hear me in person, hear me loud and clear. Can I see raised hands? Okay, yeah, I saw some thumbs up.
Yes, sir. You are audible.
Okay, cool. So let me talk about what we are really uniquely positioned to do for AI. The AI is not just yet another project for us. It's really the core of our business. At Google, we create and run our own AI models, as you definitely might have heard about. Our latest Gemini 3.
Recording in progress.
On the same infrastructure that we offer you. And we're talking about really massive scales, 1.3 quadrillion tokens served in a month and 2 billion people and increasing rapidly, interacting with products like Gemini, AI overviews, and all the other products that are infused with Gemini in the background. And critically for researchers and developers such as yourself, this is an interesting fact. 9 out of the 10 AI labs and 70% of all the funded GenAI startups are running on Google Cloud. We've seen a 12x growth in our AI infrastructure consumption, and I believe that's because we are delivering what the market really needs: superior price, superior performance at scale, at a very attractive economics. So what is the AI hypercomputer? And the AI hypercomputer is really at the center of all of our offerings. Whether you're looking at a Vertex, which is a very managed consumption model, mostly for model as a service, or when you want to build AI agents, or if you are a researcher or a frontier model builder, when you want to directly consume the lower layer entities such as GCP VMs, TPUs, and Kubernetes engines. At the center of all of this is the AI hypercomputer. It's basically an integrated supercomputing system that we put together for researchers and developers such as you. And the main goal of this is to deliver superior productivity, ML productivity, or as you might call it, the good put, not just raw speeds and feeds. AI hypercomputer is optimized across several layers. The compute layer, the storage and networking, and has the right set of open software stack, which includes all of the popular frameworks, including JAX, which we are going to focus on today between Robert and Srinath. And also it provides a set of the backend compiler that powers the ML frameworks, along with flexible commercial consumption models. By the way, a quick plug for the TPU Research Cloud, which is going to be very interesting for a lot of researchers. And I have a link for that in my very last slide. And you should definitely look at that if you are a researcher and apply for TPU Research Cloud. So we are optimizing across the full stack, software and hardware, to deliver against key use cases like training, post-training, and inference. And that's how you as an AI researcher and developer get the competitive edge when you develop on AI Google Cloud, on Google's Cloud's AI hypercomputer. So there are two accelerator platforms that form the core of this AI hypercomputer. The first one is the Google Cloud GPU. As all of you are familiar with, this is with a very strong partnership with NVIDIA. We offer a range of NVIDIA GPUs starting from the G2 for low-cost inference, all the way up to the A4 Max, which is a great GB300 system. So we're not just about one accelerator or the other, but it's a combination of both NVIDIA GPUs and TPUs. Now let's focus on the TPUs, because this talk is focused on TPUs. We've been innovating on the TPU front for a while. This is our homegrown accelerator. We're constantly driving higher performance generation after generation. The generation that is available in terms of the oldest generation to the newest is the V5E and the V5P, all the way to the latest Ironwood, which is our 7th generation TPU. Okay, V5E, V5P, they're well known for powerful, scalable, and flexible acceleration. A lot of large language models have been trained on it, both open source as well as closed source. Okay. Now, on the far right, you'll see the Ironwood. We'll talk about that in a little bit more detail in the next few slides. So you might be thinking, why TPUs? What's the unique thing about TPUs, and why are they differentiated, right? TPUs are basically, again, as I said, a decade-long journey for us. We started by looking at a chipset that was very much optimized for workloads, especially for machine learning. When we started with V1 back in 2015, it was basically an internal inference accelerator. And then we developed many models after that, all the way from V2 through the current generation of Ironwood, with a 5x increase in the peak compute compared to V5P. So we had, when we skip a generation between V5P and go to Ironwood, you're getting a 5x performance increase in peak compute. TPUs are also unique in the sense that they use fewer memory operations. They're designed specifically for matrix multiplication, which, as you all know, is the core of how deep learning works. And the memory architecture is very highly optimized for that. Robert and Srinath will cover that in much greater detail. They're subject matter experts. One of the key distinctions between a GPU and a TPU is that GPUs are essentially, they're going to have a lot of parallel memory fetches, and this creates a lot of times significant overhead. Whereas a TPU is very streamlined for large input tiles to be fetched directly from HBM into vector memory, and then to the matrix multiplication units called MXUs. Again, you will get to hear a lot of that detail in Robert's presentation as well as Srinath's presentation. So this allows us to literally, optimize on memory operations to a very high degree, typically about 99%, which also then leads to greater power efficiency and a higher sustained performance. So a little bit more detail about Ironwood, which is, again, as I said, the latest generation TPU that we recently announced. As I said, it's 5x more peak compute capacity than the V5P, but it also brings 6x more HBM. HBM stands for high bandwidth memory. Again, you will hear about how that is used and why that's important. So all of this leads to an ability to deliver models with massive footprints. And this kind of a jump, 5x and 6x, marks a step function jump in the performance, efficiency, and scalability of the hardware that we are offering. This is not just about performance, but we are also able to deliver extreme scales. What do I mean by that? As large language model developers and researchers, you can appreciate that scale is got to be everything when it comes to large language models, right? And the TPU architecture truly shines here. In a Ironwood TPU superpod, it's a massive cluster of very densely, highly interconnected 9,216 TPUs sharing 1.77 petabytes of high bandwidth memory. This architecture is built on top of our ultra-fast interchip interconnect called ICI, which gives us 118 times the high-speed shared memory scale of the nearest alternative that's out there in the market. This unified memory space simplifies your programming, and you don't have to worry about how this memory is interconnected or where it's in the pod, etc. This allows you to build really large-scale models, trillion parameter models, and on TPUs. Sorry. So you might be thinking, wow, at this massive scale, what about reliability, right? Obviously, these are machines. And machines, as you know, statistically can fail. So we have to really think seriously about what does failure and reliability mean in these large clusters. So we have developed what we call as the OCS, optical circuit switching technology, which very dynamically reconfigures the fabric for the entire pod if there is a node or two that is dead in amongst this training slice. And it reconfigures the entire slice, and it restores the workload from the previously saved checkpoint. Thereby, you're not looking at retraining or restarting from scratch. So this is the system level resiliency that we have architected into this superpod to make it truly a mission critical system for AI workloads. Now, we also innovated not just in the architecture and the interconnectivity and the chip itself, but everything from power to network and cooling efficiency. As I just said, for networking, it's fifth generation optical circuit switches that provide 12 petabits per second of connectivity with dynamic reconfiguration and maximizing utilization. Liquid cooling for 1 gigawatt of liquid cooling deployed, which is 70x the capacity of any other fleet that's out there. So these are all, and disaggregated power, over 500 kilowatts of power per rack. These are innovations, as you can see, literally across the stack, from power, cooling, interconnect to compute to storage and memory that we have delivered for building into this AI hypercomputer. Now, okay, so this is all about the hardware mostly, right? And now you might be thinking about, what about training and post-training? What is the software stack? That's where all the talk of Robert and Srinath is going to cover, mostly about thinking about all the software frameworks and libraries that we have and frameworks, and how does that really start utilizing the power of this TPUs. So, I'll just end by saying some of the largest foundation models builders across the world, whether it's Kakao Brain in Korea or Moloko or Safe Superintelligence, started by Ilya Sutskever, a leading researcher from OpenAI, etc., and Anthropic are using Google's AI hypercomputer. I think there's no other validation for what we're doing is right for these leading model providers and builders. I leave you now in the capable hands of our technical experts, Robert and Srinath. Before leaving, I wanted to give you a key set of resources to understand more about this AI hypercomputer and also the Ironwood TPU. And lastly, as I said, the TPU Research Cloud. So for researchers out there, whether in IISc or in other institutions in India, we really invite you to submit a proposal on what you would like to do with the TPU Research Cloud, and you will get free access to TPUs. That is a key thing, free access to TPUs for researchers. So we invite you to really dive deep into our technologies and engage with us. I'm very glad that Srinath is on site. So he's got deep expertise across the stack, and I'll stay back for some more time. Robert, I think we can probably switch right into your presentation.
Okay. Hopefully everyone can hear me. Let me present my slides. All right. Does this work? Is my audio okay?
I can hear your audio.
Okay, great. Hey everyone. So thanks, Srikanth, for this introduction. This was mostly an overview on TPUs. I'm a JAX engineer, and my presentation today is mostly about the combination of JAX, TPUs, how to program them. So this is going to be more of a practical, hands-on tutorial together with how you can use JAX to really unlock the power of these chips. So yeah, let's start. I want to talk in this presentation about three. And first, I'm going to cover JAX and sort of where JAX shines and what really the idea behind JAX is. Also TPUs in the second section. I don't just want to give you an overview of the chip, but also try to give you an intuition for how these chips are built, which informs what they're good and how you can really utilize them. So what is essentially how to get the most out of them. And finally, a cool connection to TPUs is Pallas, which is a JAX kernel language that gives you very low level control over the chip itself. So when you're doing research and the higher level machine learning specification that you might construct in JAX or PyTorch is not enough, you want to drop on the lower level. Kernel languages are super cool. They give you much more control, much lower level control. And Pallas is the dialect, the kernel language for TPUs. So I'm going to talk about it in a whole separate section. All right, but starting with section number 1, JAX. I work on JAX. JAX is a language for scientific computation. It's super useful for machine learning as well. It was designed to be very close to how you express math. So there's a lot of functional concepts in JAX. It's intended to be easy to work with and sort of follow the equations for machine learning networks that you might construct directly. So the point is to be sort of research friendly. It's also designed from ground up to be very hardware friendly. So when you write programs in JAX, the point is to both make it easy for you, but also make it easy for the compiler to translate that program into something that's really efficient on hardware. So these two goals are, it's quite an ambitious combination, but I want to show you what the design principles are. Many of you are probably familiar with JAX. I still want to go over this high-level overview. Fundamentally, JAX, I think one of the really cool features is that it re-implements a lot of the NumPy API. So if you're already familiar with array programming languages, specifically in Python, if you're familiar with NumPy, JAX interface often just requires switching a single import to now use the JAX lowerings for these functions. So instead of using NumPy, you can now use JAX.NumPy, and your program should immediately start running faster. And what's really cool is that while NumPy runs on CPU, a JAX program can run on any accelerator supported. And JAX supports GPUs, TPUs, CPU as well. And what's cool is that often only minimal code changes are necessary, so that these functions that JAX implements in JAX NumPy are essentially exactly the NumPy implementation when it comes to math. So it's the same functions, the ones you might be familiar with. The additional feature of JAX is that it has a lot of transformations, so functional transformations that essentially take in a function and return another. The most common example of this is taking derivatives. So JAX was essentially also built with autodiff in mind. So one of the fundamental transformation in JAX that you can apply to any function that is expressed in JAX is grad. So grad will take in a program, a JAX function that you wrote in Python, and return a function that computes the gradients through that very same function. So that's the fundamental transformation. But JAX also has a couple others. So in general, JAX was built to support transformations. And so another really powerful one is VMAP, which lets you batch your programs. So if you write a routine that operates on a batch of one or on a particular case, people have written physics engines in JAX. If you then want to generalize that to multiple objects in your physics engine, or if you just want to apply the same complicated mathematical functions that you have to a batch of inputs, all you have to do is transform your program with VMAP, which batches it, and that's it. No other code change is necessary. So no rewriting, just a transformation. These JAX transformations are designed to be highly composable. So you can add grad on top of VMAP, on top of another VMAP, and they'll all work. Here in this example, we're adding a VMAP to a grad. So we're computing the gradient of each entries, or we're computing the gradient with respect to parameters. And so we're adding this in axis to indicate that we want to batch over inputs, but not batch over parameters. The model parameters are shared, but the inputs are actually batched. Another the super useful transformation in JAX is JIT, which is a way to compile your programs. So essentially, this is the third transformation, also super useful, also super composable. And the point here is to really take advantage of the second JAX ambition, which is to express programs that are very hardware friendly. JAX JIT passes the JAX program to the compiler, and that can improve execution dramatically. So the compiler is able to fuse functions, to reuse local memory, it's able to eliminate dead or repeated code, and it's able to really, run extremely fast with essentially no overhead. And what's, I think, extremely useful both for research and computational engineering is that you're doing this entirely from Python. So no need to write any C++. This is just another JAX transformation that you just apply to your program. So the program that we had just before, a VMAP of grad, we now apply JIT, and suddenly this function becomes one that can run on any accelerator, and it'll run much faster. So JIT is actually a transformation that does two things. On one hand, it compiles, which is what I was just discussing. On the other, JIT also transforms your program into a multi-accelerator program. So if you now have inputs that lie on several GPUs or several TPUs, they're split, this JIT program, when called on those inputs, will actually distribute the computation for you. So it's an extremely powerful tool to both make your code run faster, but also to make your code run on multiple devices. Again, in this example, and this happens often in practice, there are essentially no changes needed to your actual program. So the initial math that you wrote, the initial research code that you're working with, doesn't require any edits, apart from the top-level routine being wrapped in these transformations. The way JAX works, to distribute these computations is it works with sharded arrays. So a sharded array is a pretty cool concept I'm going to come back to in just a couple of slides. But essentially, when you look at an array in NumPy, it's an array that lives on the CPU. If you look at an array in JAX, it's an array that lives on any accelerator, and it can actually live over multiple accelerators. That's a global view of a sharded array. It's a global view of an array that is partitioned between multiple devices. And so once you have data presented like this, once your neural network is partitioned between different accelerators, maybe it's split between 8 devices on a single GPU node with 8 GPUs, all you have to do is call your previously defined JIT function, and it will just run on those 8 devices. You get some extra control if you want to define, say, different prioritization strategies that you can achieve by decorating the JIT to specify how the inputs should be sharded and how the outputs should be sharded. So I'm going to talk about manual control and control over these programs and distributed computing control in a couple of slides. But you do get those the in-sharding, out-sharding control, but there's often actually unnecessary. Oftentimes when you run these examples, they're smart enough to figure these out for you. So I wanted to spend one slide on essentially showing you how JAX and the compiler interact, so how JAX works initially, and how the JAX output, the JAX produces, then ends up being passed to the compiler so it can work on top of it. So JAX is a Python framework. what it does is it traces your Python functions. So you've just moved your code from NumPy to JAX NumPy, and what happens now is JAX will introduce tracers for these, and it'll walk your program just directly in the NumPy code. This will not execute, so if you have conditional flow, you have to inform JAX of this explicitly, but because of tracing, JAX is extremely friendly to metaprogramming. So any kind of metaprogramming that you might want to do in Python, because tracing is a very simple technique of capturing the program, JAX will be able to work. You want to define a generator of functions. This is all no problem, and you'll still be able to get a JAX, a program represented in JAX. So JAX has this intermediate representation we call JAXper, which is a JAX expression. And again, one of the powerful features of JAX, you have these transformations that you can then apply to those. And then finally, the way this interacts with the compiler is the JAX JIT transforms this into a representation that is more compiler friendly, into HLO. And then that HLO is directly consumed by a compiler developed at Google, the OpenXLA compiler that can compile your JAX. This principle, hopefully this becomes less of a black box, and you can really push it. You can push the system as much as you want. You can introduce your own neural networks. You can write your own transformations from scratch too. And we think the whole framework is very well tested. I mean, it's really made to enable research. So definitely give it a try. And hopefully it's quite easy to follow what's actually going on underneath. So what I remarked on before with JIT is that JAX has this unique ability by using JIT and by using sharded arrays to achieve two really important things for scaling, especially for machine learning research, is that on one hand, you write the same program that can run on any hardware. So there's no really difference between the program you write for CPU or GPU or TPU. And secondly, because JIT is directly made to run on multiple devices, this sort of parallelization is just embedded directly into this machinery. It can run at any scale. So really, the transformation I just showed you are sufficient to train a large LLM distributed over multiple chips, because you need nothing else except JAX NumPy combined with JAX JIT. So the way this actually works, this unified parallel computing, is you have a computational graph. So say this is a neural network, it may be a linear layer, and you have two devices. What you'll do is you'll put your model parameters across these devices. So you'll use JAX, and you'll initialize these model weights across these two devices in such a way that they're sharded. And suddenly, your initial computation graph immediately becomes a distributed computing program. So no real changes needed. All you do is you wrap your routine, your forward computational routine into JIT, and you pass these sharded arrays, sharded model inputs. You shard the network weights yourself, you shard the inputs, but the computation that gets then distributed across multiple devices is something the compiler can do for you extremely well. It's extremely well tuned to focus on this. So with minimal effort and with high developer iteration, you can get these distributed computing programs to just work. First, to just get them to work really fast without any friction. But secondly, the compiler does its best, and it's really quite good at distributing the work as much as possible, so that the utilization you get out of this hardware is actually really high. And in this example, in this diagram, there's two chips, but people have easily run jobs with 10,000 chips or more. And really, again, not much changes. Your mesh of devices becomes bigger, but the program that you express in JAX NumPy and the program you wrap into JAX JIT is very similar still. So before I mentioned that JAX tries to give you levels of control. So in the example with NumPy, I showed you JAX JIT, which is the highest level over here. And I showed you these additional annotations that you could use to also tell the compiler how the inputs should be sharded and how the outputs should be sharded. So this is sort of another level. But JAX really wants to span this, this whole space from something that's fast to write, just NumPy, something that's fast to do research on, all the way down to extremely low-level manual control over the hardware, so that if you do need to exploit a particular structure in your program, or you just are more interested in those types of questions of working much closer to hardware, this is still something that you don't have to leave the JAX world for. JAX is made to give you these tools to work on any abstraction level that you might want. The other three interesting ones is ShardMap, which I want to talk in just the next section. But also we're going to talk later about the kernel languages that I mentioned about TPUs. And there's also foreign function interface addition to JAX. So you can actually run a GPU program. You can write your own CUDA kernel or a CUDA program. You can compile it with the NVIDIA compiler, and you can call that object, that function directly from JAX. So we have some NVIDIA collaborators, which, for instance, wrote their own custom nickel communication collectives, and they just called that CUDA code they wrote from JAX without any issues. So that's talking about, say, the lowest level here of control. Obviously, the more manual control you demand, the slower that thing might be to develop. But the idea is not to say that one is better than the other, but the JAX is attempting to serve any kind of need, which I think is super cool, because no matter which part of this stack you're working on, you get very direct access. So I think for this audience, you guys are researchers. The calling CUDA code directly is something you might do, but I think a much cooler transformation, cooler level of control that a lot of people are working on making better now, and a lot of people are really appreciating is ShardMap. So this is a way to actually now go a little bit away from the compiler and say, hey, I want to do manual distribution of work. I don't want the compiler to distribute the work for me. I've already sharded my inputs. I now want to actually shard computation. So instead of seeing the global view of the arrays, you are now able, using the ShardMap, to drop down one level to the local view. If you're familiar with PyTorch, PyTorch typically uses this per device view where you see the local array. In JAX, this transformation, the equivalent is ShardMap, where you can drop down to the per device view and control then how computation is divided between chips and how communication happens directly, very explicitly. What's very cool is this ShardMap is the fourth transformation I'm showing you, and it's fully composable with the other ones. So you can still use grad on top of this, and it will produce correct gradients. So you can do autodiff to this direct control over communication and computation. Let's see. So I just want to talk about this example here. So in this fairly simple example, that might actually be pretty close to how you might want to do distributed matrix multiplication. Once you're in the per device view, you have these A block and B block. You perform the actual computation on them, and this is where the chip will actually perform the matrix multiplication, and you follow that by a reduction. So because these are sharded, because each chip only has a fraction of the data, you now actually want to communicate the result. So you issue this call directly. And then finally, as you return and you exit out of the ShardMap, you're back in the global array view. So you can mix this and match with the rest of the JAX tooling. I've seen people write their whole program in ShardMap end-to-end. I've seen people, what's probably more common, use ShardMap for a fraction of the program, maybe a performance-critical one, or maybe a ShardMap for an entire layer in a machine learning function, in a machine learning module. So it's completely up to you, and it's completely composable with the rest of the tooling. ShardMap is a little bit more of a classical distributed computing view of how computation gets sharded. Again, you can rely on JIT, but if you do want control, it's directly available. What it exposes? The MPI style primitives. So you get access to psum, all gather, all to all, and ppermute. And for instance, in applications like a mixture of experts in LLMs, it's often quite useful to drop down to this view because you can perform the communication of tokens or communication of the weights directly. And this high level of control also gives you a little more control over performance. So if you really want to squeeze the most out of the chip. Also, if your background is in the scientific distributed computing, hopefully this is a mode that's close to you and that you can really leverage your experience in. So I also wanted to touch upon the JAX ecosystem. JAX itself is a core computational library, so it doesn't really have a neural network library in it or an optimization library in it. It is just this core scientific computing package that's focused on this composable transformations. It's focused on distributed computing. But if you want actual packages, if you want libraries, we have a whole JAX ecosystem. There's a lot of packages here. What's very important to us is that JAX is so well tested and so well composable that these packages that are built on top of JAX also work with each other. So just like GRAD and VMAP and JIT worked together as transformations on top of the same program and you could infinitely compose them, so that these packages built on top of JAX work quite well with each other. So we, for instance, have an NNX, which is a machine learning library. It's a new, very cool interface to Flax, which gives you this stateful view of a neural network, kind of like in PyTorch. There's Optax, an optimization library that defines a lot of mathematical optimizers. Like if you don't want to re-implement Atom yourself, if you just want to look at the equations, it's directly there. It's a very handy library. There's also Grain for data loading. Very cool because all this distributed host work of loading data is done really, really well in Grain. And Grain takes a lot of care to work very well with sharding. So if you want to read your data or in a sharded way so that you can distribute your computation well, you don't have to, there's not much overhead. Grain can configure this for you. We have Quicks for quantization, we have Tunix for RL. Definitely check it out. I wanted to show you the jax.dev website. So it's literally just jax.dev. And it's the API documentation for JAX, but I think it's not just that. Or I want to tell you that while being a JAX documentation, it also has very, very cool guides to a variety of computational topics. So we have some guides on collective image multiplication. There's a lot of cool examples. The Palace, which is a kernel language, is also hosted here. So definitely, if you're interested in JAX, but also if you're interested in general computational examples, check it out because it's not just the API. It's a bunch of very cool articles. We constantly update the website, so definitely check in. But I highly recommend it. There's of course also API reference. So if you want to look up how a NumPy function is implemented in JAX, it's all there. Okay, so now jumping to the second section, let's talk about TPUs. So Srikanth talked to you about TPUs. That was super cool. I want to take a bit of a different approach, showing you, trying to essentially give you an intuition of how they're built and what they're good at, and how really to think about them in order to get the best out of them, get the best performance out of them. So the way I like to think about TPUs is that they consist of essentially these three sections. They have very fast compute, so they can compute matrix multiplications extremely fast. The core unit for TPU, the majority of the chip, is essentially dedicated to performing matrix multiplications. It's really good at this. TPUs are also connected very well. So when they design TPUs, the design is not just on the chip, the design is also on how they communicate with each other. So the topology of the chips and the communication network between them is a very big priority because it's so important in distributed computing. And finally, this is maybe a little paradoxical, but I think a strength of the TPUs is just how simple they are. is just how focused the design is, in such a way that they both can be very good at what they do, make simplification, machine learning workloads, but it also, the uncomplicated architecture makes it so that you or anyone else that wants to make the most out of it can really easily reason about what the chip is doing, and so write a much more efficient program for it. So I think these essentially summarize what the TPUs, how I like to think about the TPUs. Srinath showed the timeline already, but Google has quite a bit of experience designing these chips. Hardware is never easy. Designing new hardware is always hard. Google has been doing it for quite a while now, starting with the first version that was never released, then the version 2 of the TPUs in 2018. What's I think extremely cool is that the version 2 of the TPU, even though it was released quite a few years ago, still runs actual workloads. So these chips are still actually used. And you can actually still use V2 chips with JAX. There's absolutely no problem with the compiler supporting that version of the TPU. So I'm not sure if they're still available on Google Colab, but it used to be a time where they're available there. I think now the newer version is available. But the chip V2 still makes financial sense for Google to run, just because it's just so efficient. Then there were versions 3 and 4. I think with the 5th generation, 6th generation, and finally Ironwood, these chips are becoming extremely powerful. And they're achieving extremely high speeds and the scale, really. Both per chip, they're powerful, but also their interconnect is very, very good. So with every generation, Google is learning how to make them better, and they're really becoming extremely, extremely powerful. I wanted to walk through a single chip. This is in my attempt to essentially try to show you how I think of them. I mean, this is nothing new, but basically a chip will consist of a couple key elements. It definitely has compute. So this chip, these numbers for MXU flops are going to be focused on how fast it can do image simplification. This chip also has very fast memory. So this HBM memory, just like GPUs, is very, very good. Say if you want to run neural network inference, that memory speed is actually one of the most important parameters you're trying to look at. So this parameter, it's not just the capacity, it's also how fast this memory is. Then the really important interconnect. So I'm going to talk about how these chips are connected in a second, but they will often be connected to their neighbors, and the speed of that link is very important when you're comparing them to alternative hardware accelerators. What's important too is when you're training these workloads, there's a certain size beyond these chips are then communicated using traditional networking, traditional data center networking. So the largest unit of the chips that are connected through the fast link, we call it pod. So if you want to train a job that is bigger than a pod, then you have to communicate over the regular data center network. So this fast speed above is just up to the pod size. So for the V6E chip, Trillium, the pod size was 256. And finally, I'm going to talk about what units are on the TPU, but fundamentally it's going to be mostly the tensor core unit, the matrix multiplication unit, together with some additional special hardware accelerators for gather and scatter operations. So despite the fact that the chip mostly focuses on matrix multiplication, it'll also have a dedicated unit dedicated for gathers and scatters, for instance, for recommender systems. These are really powerful operations. Recently, Google released the newest version of the TPU, the Ironwood. It's extremely fast. It's extremely well connected. It has even more memory, even faster memory. And what's extremely cool is that the pod size that was 256 on the V6E on the previous generation is now at 9,000. So actually, it is essentially very, very difficult to select a machine learning job that spans beyond a single pod. What that means is that when you're training your job, your entire job has access to extremely fast communication. extremely fast interconnect. You don't have to worry at all about needing to span multiple pods quite frequently. Okay, so how a TPU works, I think this is important just because, though it might seem like a detail, how a particular hardware works, especially if you're personally focused on software. But the fact that TPUs are quite simple is a huge advantage because it's much easier to reason about them and much easier to write performance software. So TPU will consist of 3 units and 3 types of memory. They'll have a matrix multiplication unit, one of the more important ones. They'll have vector units, so these are for vector operations. So say if you want to multiply 2 activations together in a gated linear unit, for instance. Everything that is not a matrix multiplication. And finally, they'll have scalar units. So TPUs are not just these sort of machines that just crunch through uniform data. They have full control flow. You can write programs that have loops with dynamic trip counts. You can write programs that have if statements in them. And the TPU has a dedicated unit for dealing with this explicitly. The way memory is organized, or actually, let me see. Yeah. So the way the memory is organized in TPU is, I've already talked about the high bandwidth memory. So it's just the HBM memory. And then the only 2 other types of memory is going to be the vector memory, which is your directly controllable, essentially cache memory. If you're familiar with GPUs might have something like the L2 cache in NVIDIA, but VMEM, the vector memory, is something you control directly here. So this is going to be the fast memory that you work with, and I'll talk more about this when I discuss PALs. And then they also have scalar memory, which is going to be used for the scalar unit for control flow and things like that. The matrix multiplication unit is really interesting. TPUs are actually, unlike GPUs, will run single-threaded. So the way the operations are executed is you just have a single thread that moves over the individual ops and executes them one by one. And despite that, these chips are able to match the other accelerators in throughput. And the way to achieve this is they have these dedicated matrix multiplication units, specifically the systolic array, which is able to stream matrix multiplication elements to inputs along this matrix multiplication unit and produce these results in batch all at the same time. So roughly speaking, in a single clock cycle or a single logical clock cycle, it's going to be able to compute a lot of elements together. There's a dedicated circuit to this. And what might seem like a limitation that the chip works single-threaded is actually a huge advantage because it both is able to compute fast thanks to this dedicated circuit, this systolic array, but also you don't really have to worry about writing parallel programs. When you program TPU on a low level, it's just, can I issue the matrix multiplication instruction now, maybe I'm going to do some conditional flow, and you don't really have to reason about stuff like race conditions or anything else. The chip is still very fast despite running single-threaded. The interchip networking is super cool. The chips are usually actually organized in either these 2D square pods or 3D cube pods. And basically each chip is connected to its neighbor, but also they often have wraparound connects. So a chip at the edge of this grid will have a cable wrapping around, and it will and the chip, sorry, just looking up a message. And so if hopefully you can see my mouse, if I'm talking about the chip on the bottom right, that chip is not able to just communicate with the left and the chip above, but also with the neighbor all the way on top and all the way to the right, or all the way on the left. And these interconnects are again, you can look up the numbers, the actual statistics for them, but they're extremely fast. And this is really what allows the scaling. If you want to go between 2 pods, so if you're, say, working with Trillium and you want to have a job that has 512 chips, you can communicate between these pods with the regular data center networking. So there is, there's the possibility there. These interconnects were designed in such a way, this was always the goal, to achieve near optimal scaling in large distributed workflows. So when they were testing, they continue to test this, they continue to do this performance benchmarking, but for neural network training, it's essentially possible to achieve a near optimal scaling. So as you add twice as many chips, the throughput of your job is essentially not 200%, but say 199%. It's extremely close to linear scaling, which makes it extremely attractive to add more chips and then unlock the ability to train either larger networks or more data. You really not, thanks to this really ingenious networking, you're really paying no penalty as you add more and more chips, which is extremely cool from a systems perspective. And these are actual numbers, so these come from actual performance tests where they train an actual model to see how well these pods after installations scale. IOMOD in particular, like Srikanth was saying, has this new advantage that the pods here, the unit that is able to achieve this scaling, is very, very large. So unlike previous generations of TPUs, you have access to 9,000 TPUs here. And that essentially means that wraparound thing that I was talking about is directly available on that scale. This generation 2 is organized in a 3D geometry, so you have access to 6 neighbors for every chip, and these very fast links. Of course, when you provision this, I think I want to talk about this from a sort of more practical standpoint. If you want to use these chips for TRC, or if you're starting your own company and you want to become a customer, you provision the chips by asking for a subslice. So you can ask for the full pod, or you can ask for a subslice of the full pod. So I can, for instance, request a 2x2 topology or a 2x2x2 topology to slice out smaller numbers of chips from the full pod. And what's very nice is that these chips are connected or actual host VMs are connected to only a small number of chips. So each host will be connected to, for example, only 4 TPUs. So if you provision 64 of them, you end up with quite a few hosts, which makes it much easier for, say, data loading. You're no longer going to be bottlenecked by a single CPU. You now have access to a number of CPUs, both of which are very powerful machines. So these are some numbers for Trillium, which is the V6E generation. I think there's maybe like 90. It's a 96 core CPU or something like this. It has 700 gigabytes of RAM, and it has very efficient network storage. So if you're accessing data from a Google bucket or a network disk that you attach to these, it's very, very fast. So I mentioned this before. I now have a better figure for this. I wanted to talk to you about specifically the memory units on the TPU. So I talked about the compute unit, which is the matrix multiplication unit, the vector unit, and the scalar unit. But the memory hierarchy is also super important. So there's this HBM memory, which is quite intuitive. And the way TPU operates is, and this is not essentially an optimization. Any programmable TPU, the way it will always work is it will start with the HBM memory. It'll then load chunks of it into the vector memory. The vector memory can be operated on by both the matrix multiplication unit and the vector unit. And you'll then perform any of these operations in the actual hardware, and then we'll put it back into vector memory, and then that vector memory result will then be stored back into HBM. And knowing this model is super useful for actually programming these chips. A lot of this is handled for you. So when you're using JAX, the compiler will, if you're using JAX and say you're issuing a matrix multiplication that's say 8,000 by 8,000 for the result, the compiler will construct this TPU program for you. So it's not that you have to do this every time yourself. This will be done for you. What's interesting is that you have access to, for instance, really cool fusions. If I now perform a matrix multiplication and I scale the result by a certain constant, or if I multiply my result with some other result, the compiler can actually fuse these, and so that value, when it's being operated on, never actually goes back to HBM until all operations have been computed on it. So you're fusing two operations, everything happens in the fast memory, and the result is then written only at the end. So that actually makes it run often much, much faster than expected if you were to just run each individual operation and store into HBM every single time. Yeah, for sure. Let me finish this. I'm not entirely sure how I'm on time. Let me finish the TPU section, just one more slide, and we can break before the palace section. Finally, when it comes to memory units, there's also the scalar unit, which, again, full control over conditional flow. So yeah, in summary, the way I think about these TPUs is that you essentially get these three things. You get super fast chip compute, you get really good networking, and you get really this architecture. I know that it might seem like a lot of details, but this is essentially it. The previous slide on the fact that they have these 3 units and 3 types of memory is all you need to know about the hardware to achieve literally 100%. When you're working at on a large-scale machine learning job, the knowledge of this architecture, what I just presented to you in 5 minutes, is enough to get to use these chips for extremely large workloads, which I think is very cool. I think it's very cool when hardware is so focused and so friendly to the software. Okay, so the last section I have is on Palace, which is on programming TPUs, but we could definitely take questions now. Yeah, that'd be good.
Any questions? Yeah.
Hello, Mr. Robert. Am I audible?
I think so, yeah. I heard something.
Am I clear?
Yes.
Yeah. So, first of all, I would like by thanking for facilitating this workshop. I think the presentation is presented really well. And my question was with the TPUs. Like even here, I can see the peak compute per chip in the specification tab. It shows for int 8 and BF16. And this also like with the fact that if you've heard of Google Coral, the Edge TPU, right? Even in that, it only allows for inference on 8-bit models or quantized 8-bit models. Is there a reason like why FP32 and higher precision are not supported on TPUs, if my understanding is right? Thank you.
Yeah, absolutely. It's a very cool question. It is fundamentally a hardware decision, so a hardware designer decision of what type of units they want to support. Generally, the lower the precision, it's possible to make the chip run faster. And so people are always going for some form of a balance between precision and how fast the hardware can run. Typically, the BF16 is the way most of these operations are done on TPU. So they'll be typically the default precision. It's obviously half of what FP32 allows. This is an nth generation of the machines, and this was the hardware design balance. You can still perform FP32 products on TPU. It's actually a really cool technique. You need about 3 BF16 multiplication to get an approximation to an FP32 multiplication. If you split the mantissa, you can essentially simulate the FP32 matrix multiplication directly with BF16. In practice, if you were to introduce FP32 units, they would use more silicon area, and so it's probably more optimal to try to simulate these computations with a single BF16 unit. than it is to introduce explicit circuits for those. Yeah.
Sure.
When it comes to even the lowest precision, those prove quite useful in LLM training. And so that's been the direction of this hardware design or co-design for a while now. I don't know what uses actually FP8 as a unit for FP8, but most of the previous TPUs have units for int8. So the floating one is BF16 always, but the quantized one depends on the generation.
Yeah. Thank you very much.
Any more questions? We have one more.
Hi. I actually use the Julia ecosystem as well as JAX. So with the advent of SciML, actually, like the scientific machine learning is even coming to industries. Industries is actually used to this data protect and everything in Windows. So what I find with JAX is that it is like not supporting GPUs and all in Windows. So I am like as per me, there is like use cases for both JAX and Julia ecosystem for different use cases. But I am as of now, I am forced to restrict myself to Julia ecosystem for most of the GPU use cases. So is there any plan that JAX is planning to implement its like JAX GPU on Windows?
Yeah, that's a great question. In general, there's definitely plan to support as many accelerators as possible. The support for operating system is a little trickier in the sense that managing the build system for this is tricky. We have a lot of build engineers helping on this, but if it's not supported, it's most likely because it's just that there's too much work, not enough people. I don't think there's an explicit decision to drop any kind of support on this matrix. The one thing, it'd be definitely great if it worked. Definitely feel free to open an issue on GitHub if you think something should work. Specifically for TPUs, because they're so because of the networking and because of data center deployment, they'll always be connected to a Linux machine. So there, the window support is unlikely. But for GPU, yeah, it's a good question.
Robert, can you clarify that actually JAX for GPUs is a supported thing, and there's a lot of customers using GPU? I know this question was different, but what JAX is.
Yeah, JAX GPU is absolute priority. So the support for GPU and TPU is, we don't distinguish, both must work. It works extremely well I've used it in my research on GPU. It works really well for Google's customers on GPU. I recently see someone using JAX on Twitter very well on AMD GPUs as well. So the support is extensive. The operating system is I'm not as familiar with. I'm not as familiar with which builds we have right now. JAX is a fully open source framework, and on GPU it's fully open source, both the compiler and the JAX side. So it's always possible to try to compile yourself. Yeah, it's fully open source.
Hi, Robert. Ronak Berdia from Shell. Thanks for the nice presentation. I have one question. I heard some of the things that you say about what can TPUs do. Want to know what is the difference between where does GPU perform better than TPU, and what are the operations that we shouldn't be doing on TPUs?
Thanks for that question. That's a really cool question. TPUs are definitely much more focused on matrix multiplication workloads. So when talking about matrix multiplication type workloads, like say neural networks, GPUs and TPUs actually recently adopted very similar strategies. NVIDIA's hardware also has these systolic array units that tackle the problem of how to multiply matrices very, very quickly. Now, NVIDIA is an extremely well-experienced company. The chips they're making are really, really cool. They're miraculous how complicated and how well they work. NVIDIA's experience specifically on vector workloads, if you're talking about highly heterogeneous workloads where the SM architecture it works much better, is something that TPU is just not focusing on. So if you're thinking about highly operations where you might compute still parallel operations, but where you might compute different chunks very dynamically, very differently on a very low level. Because again, TPUs also support conditional flow. The GPUs have many, many more years of experience there. When it comes to a lot of machine learning workloads, and especially modern workloads, convolutions, American multiplications, attentions, TPUs definitely focus on that. So they are very, very competitive. Yeah. Good. All right. So we've been talking about how JAX works and how TPUs work. And I think it's important to, before going into the kernel language, it's the last part of this talk, the kernel language used to programming TPUs. I wanted to essentially revisit how JAX and TPUs combine. So specifically, simply how do you program TPUs with JAX? So the way this typically works, I had the slide earlier going into more depth about how the JAX expressions get created, but essentially it's NumPy that you wrap in JIT or other transformations. That transformation, JIT specifically, then is able to expose this representation that the compiler can consume. And in this case, for TPU, the compiler will just generate the TPU assembly directly for you. So you produce your JAX program, you JIT it, and it'll just then get passed through the compiler to run on the TPU. But this is it's not just JAX. The representation for the compiler can be produced basically with any framework. This OpenXLA compiler, as long as you can provide this representation for it, so either using PyTorch or JAX, it's able to then target a vast array of different hardware. So CPU, GPU, TPU, and this is all the magic of the compiler. It's the ability of the compiler of transforming these intermediate representations into an actual assembly code for any particular hardware. If you're talking about NVIDIA GPUs or if you're talking about AMD GPUs, it fundamentally needs a different, they end up needing a different assembly language, and the compiler is able to do this with the same JAX program. So we had a question earlier about the GPU work and CPU work. The promise of JAX is to be able to write the same JAX program and ideally deploy it on any accelerator very quickly. I saw some people recently, I worked with some people recently writing physics simulations in JAX, and they often find that when they want to deploy a single simulation, not in a batched way, CPU works the best for them. So that they'll deploy the same code and use the CPU actually for execution less than the GPU. Here's an example of how a compiled program works. So Google has a very mature set of profiling tooling as well. So it's not just that you can run the code on the TPUs, you can actually see in depth what's going on. So here, this is an example of a decoding in an LLM. And there's two takeaways from this trace viewer. The reason why I wanted to show you this example is on one hand, you can see just how many different operations the compiler performs. So the top level here is the line that the TPU executes at any given time. You can see there's this decode ragged dot block that the compiler or the machine is spending a lot of time on. There's a bunch of smaller operations, but realistically, what's really cool is that there's both a lot of ops, and these are on the nano or microsecond scale, but also this ops that are presented here are actually way fewer than what I was programming when I was programming this program, because the compiler is able to fuse a lot of these functions together. And just like we were talking about the memory architecture of the TPU, where it has the HBM, but it also has this very fast on-chip memory, VMEM. A lot of these, say when I multiply 3 arrays, they don't actually get stored back, they immediately get fused by the compiler. So you end up with a program that is much faster often than what a naive roofline analysis would indicate. So yeah, it's a very, very powerful tool. So yeah, here is an actual LLM decoding. What's another interesting thing to see here is that when you see the top level, so this is 2 lines for one TPU and then another on the bottom. The narrow top lane is the actual operation executed by the TPU. And these are simply namescopes. So these are debugging information that's useful for performance debugging. But the top lane is actually a single lane. And this goes back to what I was saying, that a TPU executes single-threaded. So actually this whole program is done one by one. There's no overlap. There's no overlap needed, essentially. Okay, so yeah, let's talk about the Palace. Let's talk about Palace, the kernel language for TPUs. And so Palace essentially forms an alternative to JAX and HLO. You no longer have to rely on the compiler. You might want to, you're doing research, you know much better what you want the hardware to do than the compiler. You want to take manual control. That's fully supported. And this is why Palace, with Palace, you can actually talk in hardware concepts directly. So you can write Palace programs that tell the hardware on a very low level what to do. It still goes through a TPU assembler, so there's still a compilation stage, but it is a different compiler. It's a much, much lower level compiler. So what you write in Palace is essentially you tell the TPU what to do directly. This is sort of in contrast to this JAX flow with the transformations and intermediate representation. In Palace, you'll write the kernel to work directly. This goes back to this figure of different levels of manual control in JAX. You're now in this kernel languages, so on the red dot. Because in this presentation we're actually talking about TPUs, what's very cool about TPUs is that the FFI interface, so writing something like low-level C code, is completely unnecessary here. Palace is actually how top AI labs will write very low-level code on TPUs. They won't actually write C code, even though in the GPU world, definitely if you want the most control within the GPUs, you'd write CUDA. But on TPUs, Palace, this kernel language that I'm hopefully going to show you a sneak peek of, is the way you can talk to your hardware. It stems from the combination of both the team being very careful about how to design Palace, so that it's both easy to write and low level, but also from the fact that this TPU architecture is really focused on performance and being friendly to programming. So there's just no need. So why Palace? To be honest, a lot of the time the compiler and JAX and the top level representations are more than enough. You can still do a lot of performance work just on the JAX level. You don't need to rewrite stuff in Palace. But if you want more control, if you want to control the hardware directly, maybe if you want to exploit a specific structure in your program. So we often work with dense arrays, but that's not all there is. Lots of fields have sparse arrays. And so one way to do this in JAX is to still have a padded array of values, where sparsity is represented with some additional metadata, and being able to skip this computing over the empty space with something like a lower level program written in Palace. So this TPU assembly that you're going to be generating with Palace is definitely much, much lower level than HLO. HLO is what JAX generates. And some really cool applications in, say, from the scientific computing world is block sparse linear algebra. People have used Palace to write mesh multiplication in like the BCOO format. So where this is not an element level sparsity, but this is block level sparsity. Some of that research inspired mixture of experts routines. So mixture of experts is definitely very relevant to LLMs these days. Also helps a lot. Palace helps there a lot, especially with the core GMM routine. Palace is not just for compute; it also gives you access to a level of communication routines. So if you want to do custom communication, just like in ShardMap, you can use these MPI collectives. In Palace, you can write your own collectives. And finally, TPUs, like I said, despite being major multiplication machines, they still definitely have these the conditional flow units. So you can make use of extremely low-level loops. You can have if statements and so on directly in Palace. If you're familiar with Triton, Palace is another kernel language, but it tries to be a little more low-level. So both Triton and Palace give you access to this manual computation and some of the memory control, but Palace focuses a little more on the explicit software pipelining. So there's a couple dialects, but all the dialects that are expressed in Palace will try to talk about the memory pipeline directly. So what the memory pipeline is how the TPU operates. So this is a slide from earlier, and the point of the memory pipeline is to make that flow from HBM to VMEM through the compute units, back to VMEM and back to HBM, make it explicit. So in Palace, you'll write the core computational routine. So that's the first step, the fact that this is a low-level kernel language. This is some pseudocode example. But you would also write is you would actually explicitly write the memory pipeline. So what I'm doing here is on the top, I have the kernel, the actual kernel code that operates on references to these VMEM values. So the ones that are already stored in the very fast memory. So when I add them together, there's no memory copy. Essentially, because they live in such a fast memory, this addition here happens almost instantaneously. On the other hand, when I call this Palace from JAX, I have to specify in what order these blocks should be traversed. So these are these block specs, and what they specify is you need to specify two things: the size of the tile that will get copied from HBM to VMEM and then back, and also the map. So as you have grid implications, how it will traverse these tiles over the bigger array. Again, what's cool is that because TPUs are single-threaded, this will happen sequentially. So if you want to store values for a future invocation in this grid, so here we're n by n, say we're 16 by 16. If I want to store a value for the next iteration, I can just store it in a persistent VMEM reference, and the next iteration will directly get access to it. This is a little more interesting example because this is a matrix multiplication. The kernel becomes extremely simple. What you're doing here now is just multiplying these two arrays. You could have used the add operator or JNP ... but in Palace, you actually have to be explicit about data types. So the reason why it's not just JNP ... the regular matrix implication, is here we also want to be explicit that the result of two BF16 inputs is actually float 32. And so when I wrote this kernel, I requested that output. And so I need to use a routine that generates FT32. This is a way for you to really talk to the hardware unit, because the hardware unit can do BF16 times BF16 and a float 32 accumulator. This is my kernel. But the kernel is simpler than the addition kernel. My block spec is a little more complicated. Now what I'm doing is I'm essentially traversing this matrix in these blocks over the reduction axes, and I'm accumulating the result. I like this example a lot because there's, I don't know how many, 15, maybe 20 lines of code here. And this example, when you tune the tile sizes, can actually be as fast as what the compiler generates. So you've just written 15 lines of code that match the performance of an entire compiler that tries really hard to be really good at matrix simplification. So Palace, the focus of Palace is really the developer friendliness. So that you don't have to write a lot of different. This is state-of-the-art matrix simplification. There's really not that much else to it. I think when I tuned it, I achieved something like 96% of the specs of the total peak flops that are in the datasheet. There's you can also do communication Palace. So this is an example of just a very chaotic, some form of message passing between two TPUs. And the way this is done, if you're familiar with the with distributed computing concept, this is essentially just an RDMA. So it's a remote direct memory access. The TPUs can access each other's memory, and so in Palace, the way it looks is you just address another TPU. This is still written in the SPMD style, which is why it needs this maybe slightly odd-looking if statement. But this PL1 is just an if statement, but written in such a way that it is tracer-friendly. Palace is also traced, just like JAX, which means that all the meta-programming techniques that you might want to use in Python are still fully compatible. You can use global variables, you can use list comprehension. Of course, when you're actually writing computation, you have to make sure that it's traced. But I, for instance, found that when writing a routine like this, a communication routine, it was super useful to write a function that actually writes or has a template of a communication, of issuing a communication, and I can then make this code look much cleaner. Because, again, Palace doesn't care, the program is just traced. This is an example of an all-gather. So in this pod, people often do these all-gathers extremely efficiently, because all you have to do is make sure that all the chips have the same amount of data. So you can pass these data chunks to your neighbors, and you can do this in Palace directly. Cool. And that's essentially everything I had about JAX, Palace, and TPUs. I really like this figure because this really lets you pick any point here and make and achieve your research goals as fast as you can. If you're working with Palace, this level is essentially the lowest you go. And this is because this kernel language is designed with modern accelerators in mind. What I discussed today was a TPU dialect, but we also have a GPU dialect that's also extremely focused on performance. Yeah. The author of the GPU dialect, Adam, pays a lot of attention to performance. So there, you can also use the Palace GPU dialect to write extremely performant kernels for GPU. And I hope that I showed you just how focused TPUs are today in terms of programming. They really are attempting to be very extremely performant, but also very easy to control.
Let's take a few questions.
Mm-hmm.
Hello, can you hear me?
Yeah.
So a pretty basic question regarding RDMA. So the GPU has something known as GPU direct and GPU direct storage over RDMA, just to avoid the GPUs from starvation for data. Do TPUs also have some similar alternatives, like, for faster access, like, especially when we are dealing with a large amount of data and training larger models, or maybe even simulations?
In general, the RDMA is handled by an explicit communication unit. So what that unit will do is it will send data from HBM to another place in the HBM. This makes it essentially possible to overlap any other operations. But to try to answer your question as best as I can, on TPU, the point would be to issue this pipeline as efficiently as possible, the HBM to VMM pipeline. So as long as you can make sure that the host CPU places enough data in HBM, and then you can make sure that the HBM bandwidth is fast enough to then feed the VMM pipeline, you'll achieve full utilization. But there's no additional tricks. It's just that. When the additional element of the RDMA is through HBM. So an RDMA will head to an HBM, and then your pipeline might read from that HBM after it's indicated that it's done.
Okay, thank you.
Maybe one last thing about the memory pipeline is that you can actually write the memory pipeline in software. So Palace gives you access to direct copies between HBM and VMM. Mm-hmm. And I've worked with toy programs before where you can write direct Python code that starts a copy while you're still working on the previous VMM slice, just so that you're never stalled.
Thanks.
Cool. I have one last slide with some resources I wanted to quickly show you. I was trying to focus on the connection between JAX, TPUs, and Palace today. The couple of resources that I highly recommend is, again, the website, jax.dev. Lots of API reference, but also really cool guides that I found extremely interesting. We have a website called JAX Stack, JAX AI Stack, which is used for the JAX ecosystem. So if you're looking at packages for optimization, for machine learning, this is a website that will have really good guides about how to install not just the core computational software, but also the packages that you might need for machine learning research or optimization research. And finally, I highly recommend the JAX scaling book, which goes in detail about how to train distributed models, how to manage distributed computation in general, but also in the context of TPUs and in the context of JAX. Right. Thanks so much for listening. I might have gone a little over time, but it was a real pleasure talking to you today.